This video is about related rates, or in some books it's called time rates. We'll be dealing with some practical applications involving rate of change of related variables. Because this is an application of the derivative as a rate of change, we will always be differentiating our variables with respect to time t. I will also be giving you a step-by-step procedure on how to solve problems on related rates. Now let's have the first example. A 13-foot ladder leans against the wall. The foot of the ladder begins to slide away from the wall at the rate of 1 foot per minute. When the foot is 5 feet from the wall, at what rate is the top of the ladder falling? Now it's better if we draw our scenario here so that you may visualize it. So let's draw the figure of the problem. Alright, so this is the wall. We have here the ground, and then side view of the ladder, 13 feet long. Now we can visualize the scenario, we can answer the problem. So that we may understand each other better, we should start by defining our variables starting from time t. Alright, so step 1. We'll start with our variable t. Let t be the time elapsed since the foot of the ladder started to slide away from the wall in minutes. It's also very important to include the unit of measure that we will be using. So in this case, we'll be using minutes because of the given unit here in our problem. So we have here 1 foot per minute. So it means to say that we will be using minutes for time t. To identify the other variables, let's go back to our figure. As the foot of the ladder starts to slide away from the wall in this way, what else changes in the scenario? Of course, the distance of the foot of the ladder from the wall changes as it slides away from the wall. So let us define that variable. I'm going to use the variable x because it's a horizontal distance. So let us define x as the distance of the foot of the ladder from the wall, okay, in feet. So it's important again to include the unit of measure. So after t minutes. Okay, are there other variables in our problem? Of course, as the foot of the ladder goes away from the wall, the top of the ladder also goes down, okay? So it means to say that the distance of the top of the ladder to the ground also changes. So this time I'll be using the variable y because it's a vertical distance. So let y be the distance of the top of the ladder to the ground. So also in feet, you have to be consistent with the unit of measure. So after t minutes. Alright, so we only have 3 variables involved in our problem here. So we're done with step 1. Now let's go to step 2. Write down numerical facts about the variables. So we need to write down the given. You already have here the length of the ladder, 13 feet. And then it says in the problem that the foot of the ladder begins to slide away from the wall at the rate of 1 foot per minute. This is the rate of change of which of the 2 variables, x and y. Now because x is the distance of the foot of the ladder from the wall, so this is the change in x, okay? So this is dx over dt, the change in x with respect to t, equals 1 foot per minute. Alright. Okay, now when the foot of the ladder is 5 feet from the wall, at what rate is the top of the ladder falling? Alright. So we have here the numerical fact about the variable x. We're done with step 2. Now we go to step 3. Write down what you wish to find. Okay, what do you want to find? The question is, at what rate is the top of the ladder falling? We are being asked for a rate of change. rate of change of y, because we are being asked to find the rate of the falling of the top of the ladder. So we are being asked for dy over dt, rate of change of y. What is this? Okay, when, look at the problem, the foot is 5 feet from the wall. Alright, so when the foot is 5 feet from the wall, that is x equals 5 feet. Okay, so we are being asked to find dy over dt when x is equal to 5 feet. Alright, we're done with step 3. Now we'll go to step 4. Step 4 is write an equation to relate the variables. Aside from variable t, we have two variables, so x and y, both distances. So we have to write an equation that will relate both our variables x and y. Okay, looking at the figure here, we have created a right triangle. So this is a right triangle over here. Okay, and if we have a right triangle, we can always make use of the Pythagorean theorem. Let's see if the Pythagorean theorem will work here. So in our figure, and in our step 1, in the definition of our variables, this is x, and this is y. Alright, so using the Pythagorean theorem, that in that triangle, you'll have the sum of the squares of the two sides, so that is x squared plus y squared, is equal to the square of the hypotenuse. The hypotenuse measures 13 feet. It's constant. The length of the ladder is always 13, so it's 13 squared. Okay, so there we have the relationship between x and y. So simplifying, we'll have x squared plus y squared equals 169. So what we need to do in step 4 is to write an equation that involves all the variables aside from the variable t. Okay, and we have it here using the Pythagorean theorem. Alright, now let's go to step 5. What is step 5? Step 5 is you have to differentiate both sides of the equation that we have created in step 4 with respect to time t. As I mentioned a while ago, we will always be differentiating our variables with respect to time t. Okay, so differentiating, we will have on the left side the derivative of x squared plus y squared with respect to time t. So using power rule for both terms, in the first term, using power rule, we'll have 2x times the derivative of the base with respect to time t, and that is denoted by dx over dt. Okay, plus the derivative of y squared with respect to time t, using power rule, that's 2y times the derivative of the base, that's dy over dt, equals 0, the derivative of the constant. Okay, now simplifying the equation by dividing both of its sides by 2, we can simply have x times dx over dt plus y times dy over dt equals 0. Okay, remember we are solving for dy over dt over here, and you are given the value of dx over dt, that is equal to 1 foot per minute, and then you are given x, that is equal to 5 feet, and then we can find y by using the Pythagorean theorem. Alright, so let's do this. I will write step 6 over here. Oops. Step 6 here. Okay, substitute known variables. So I will be substituting 5 for x, 1 for dx over dt, and then solving for y after that. Right, so from this equation, x is equal to 5. I'll eliminate the units first. Dx over dt is 1, plus y, where y is unknown, still, times dy over dt, which is another unknown, equals 0. Okay, but what is y when x is 5? Okay, according to our Pythagorean theorem, from our given triangle, you have x squared plus y squared equals 169. Alright, so you can solve for y squared by transposing x squared to the right side of the equation, and that's going to give you y squared equals 169 minus x squared. But we are solving for y, so simply get the square root of both sides of the equation. Y is equal to square root of 169 minus x squared. This is actually plus or minus square root of 169 minus x squared. So substituting 5 for x, you'll get the value for y. Y is equal to plus or minus square root of 169 minus 5 squared, which is 25. So that is square root of 144, and that will give us plus or minus 12. Now, the sign doesn't really matter here. It just indicates the direction of the movement of the top of the ladder. Since the top of the ladder is falling, so we might as well take negative 12 for the value of y, just to indicate that the ladder is going down. The top of the ladder is going down, all right? Anyway, the rate of change should always be positive because a negative rate of change will just indicate that the object is moving to the other direction. Okay. Now, if we take negative 12 and substitute it in our equation, so we now have 5 times 1. Okay, so taking negative 12 for y, that's going to give us minus 12 times dy over dt equals 0, right? Let me bring this down. Okay, now solving for dy over dt, because that is our unknown, transposing negative 12 times dy over dt to the right side of the equation, you'll have 5 equals 12 dy over dt. Now dividing both sides of the equation by 12, we'll get dy over dt. Our answer equals 5 over 12. And the unit of measure would be, because this is the rate of a rate of change, would be in foot per minute. Okay. Remember that we have already considered the top of the ladder falling down, so the direction of this is downwards. So we can include the direction downwards. Okay? Take note that if you take positive 12 for y, you will be getting dy over dt in negative 5 over 12. And that indicates that the direction of the top of the ladder is going down. Okay? Because by taking y equals positive 12, remember you have not yet considered the direction of the movement of the top of the ladder. So it will show in your final answer that the top of the ladder is going down. Okay? But nevertheless, your answer for the rate of change of the top of the ladder, it's 5 over 12 foot per minute, okay, going down. So that's it for number 1. That is our final answer. Okay? Get ready for example number 2. Let's read the problem. A light is hung 15 feet above a straight horizontal path. If a man 6 feet tall is walking away from the light at the rate of 5 foot per second, how fast is his shadow lengthening? Okay, let us draw the figure of the problem first. So it looks something like this. You have here the light. Okay, this is the man. This is his shadow. Alright. So light is hung 15 feet above the ground. Okay, above a horizontal path. And then the man is 6 feet tall. Okay, walking away from the light. Walking away from the light. Okay. At the given rate. So how fast is his shadow lengthening? Well, is the shadow lengthening or shortening? Let's find out. So if the shadow is lengthening, our answer would be positive. If it's shortening, then our answer would be negative here. All right. Just to be guided, I have here at the bottom the steps. Okay. So step one. Let's start here. Let's define the variable starting from t. Let t be the time elapsed since the man started walking away from the light. Okay, in seconds, okay, because you're given the unit of time in seconds in the problem, okay? So for start, we have to be very specific about our definition of the variables, okay? But you can make this shorter once you've already get the idea of why we are doing the steps, okay? Now, what is another variable? What's another variable involved in the problem? Let's see. So the length of the shadow is changing here. The shadow of the man is the length of the shadow of the man is changing as he walks away from the light. So let that be. Let's make use of x or whatever. Okay, let x be the length of the shadow of the man. So in feet, okay, in t seconds. What else is changing in the problem as time passes? All right, of course, the horizontal distance of the man from the light. Horizontal distance of the man from the light. Okay, is changing as he walks away from it, right? Let's use another variable. So we can use x, we can use z or y, whatever you like. So if we use y, define it. So y is the horizontal distance of the man from the light, in feet also, in t seconds. So nothing else changes in the problem. The height of the man, of course, does not change. The height of the light from the floor does not change also. So we're done with step one. Now let's write down numerical facts about the variables. All right. The height of the man is 6 feet. The light is 15 feet above the ground. They don't change anyway, so they're just constants, okay? So the man is walking away from the light at the rate of 5 feet per second, 5 feet per second, okay? 5 feet per second. So what is that? The change in y with respect to t, or is that dx over dt? So the distance of the man, of the horizontal distance of the man from the light is y, right? So this must be dy over dt. So dy over dt is given. It's 5 feet per second. So everything's complete for step 2. Now we go to step 3. Write down what you wish to find. What do you want to find in this problem? So how fast is his shadow lengthening? How fast means a rate of change. So the length of the shadow is defined by x, okay, represented by x. So we will find dx over dt, okay, in this problem. All right. So what is step 4? Write an equation to relate the variables. So we have the variables y and x here. So we have to write an equation relating the two. Now if we try to look at our figure, we have here two similar triangles. We have here a big triangle whose base is equal to x plus y and whose altitude is equal to 15. Okay? And we have here a smaller triangle. Alright, this is a smaller triangle whose base is x and whose altitude is 6. Okay, so we can use ratio and proportion, okay, to relate the variables x and y. Let's start with the ratio of the altitude to the base of the big triangle. Okay, so big triangle, I'll use yellow. Altitude is 15. Eliminate the unit of measure first, and then the base is x plus y or y plus x. Right? So equate this to the ratio of the altitude to the base of the smaller triangle. So I'll use red. The altitude is 6 feet. Okay, our units are consistent, so over its base, which is x. All right. Now let me just do cross multiplication, and we'll have 15x on the left side, and then that's 6 times x plus y, so we'll have 6x plus 6y. And then transpose 6x to the left just to combine 15x and 6x. We'll have 15x minus 6x. That will be equal to 9x equals 6y. We can actually divide both sides of the equation by 3 because 9 and 6 are both divisible by 3 to simplify, just to simplify the equation. So it's going to give us 3x equals 2y. Okay, so this is the relationship between x and y. We're done with step 4. Now we go to step 5. All right, in step 5, we'll differentiate both sides of the equation with respect to t. So that is, on the left side, 3 times the derivative of x with respect to t. And that is denoted by dx over dt. On the other side, it's 2 times the derivative of y with respect to t, denoted by dy over dt. Okay, we're done with step 5. So now in step 6, we'll substitute known values. You are given dy over dt equals 5, and we are solving for dx over dt. So we'll just substitute 5 for dy over dt. So that's 3 dx over dt equals 2 times 5. Okay, so that is 3 dx over dt equals 10. Solving for dx over dt, we'll just divide both sides of the equation by 3, and we'll get dx over dt equals 10 over 3. And that is in feet per second. So the shadow is lengthening at the rate of 10 over 3 feet per second. All right, this is our final answer. Okay, now on to the next video for the next example.